It's all mixed now.
I was like, oh. It was just back in. I'm deliberating till someone again.
Not here.
Go. So Thursday. Friday.
All right, so we're going to begin with a recap of where we were last time. So we are thinking about membrane transport. We've learned about our chemical driving forces, our electrochemical driving forces, and our electrochemical driving force, adding the two together. And so we started moving into discussing types of transport, which we're defining as passive or active, depending on whether they go with our driving forces or against those driving forces. So we also spoke, as we were doing this, about a little bit about rates of transport. So we also want to know factors that can influence how fast something gets transported. So transport moving across a membrane. So when we're talking about rates of transport, we're talking about how fast you can get how much of that thing across the membrane. I left these slides in because we talked about passive transport and we talked about our three types, our simple diffusion, facilitated diffusion, and our diffusion through channels, as well as those rates of transport measured. So our simple diffusion was just going directly across our phospholipid bilayer. Our facilitated diffusion was going through a carrier protein, so a protein that changes shape and moves something across, still a type of passive transport, and we are going with our gradient. And we began to speak about diffusion through channels, going through a channel protein, which is very like a carrier protein, except for you don't need to have that shape change, that pocket moving back and forth. We're just acting like an open door. It's often going to be what we're talking about when we're talking about ions for TP. So that means we're ready to move on to active transport. Covered all those types of passive transport. So whenever we're thinking passive transport, we're thinking no energy needed. We're going with our gradient, with our force. Active transport is just going to be the opposite. So if you can identify what driving force there is across the membrane, you can figure out which direction your molecule or your ion wants to go. If it's going the opposite direction, then you know you have active transport and you just have to figure out which type. So active transport is not spontaneous because it requires the input of energy in some or at some point in time is another way we can think about that. So whenever you see something, whenever you see a protein in a membrane referred to as a pump, that is an indicator that you are looking at active transport, that you are pumping, you're pushing or pulling that substance across the membrane. Pumps really kind of like our carrier proteins, but we're using energy. We think about active transport as having movement uphill. So when we say uphill, we really mean we're thinking about something without a charge. We're thinking up the concentration gradient, so against the chemical driving force. We're thinking about something like an ion with a charge. We're thinking against the electrochemical driving force. We're going uphill, up our gradient against the way that the molecule or ion wants to go. So here we see active transport from time point 1 to time point 2, kind of. So we're beginning here with active transport pulling or pushing our whole triangle thing here from one side to the other. Whenever your book puts a red arrow through something, that's also indication that it's active transport. Just so you know, there are some conventions for colors that they use. Red is going to be active, green is going to be passive whenever you see that in images. This is going to be active transport because you look like we're starting out with equal concentration. We're creating a gradient, right? So we're starting with this equal concentration. So we would expect there to be no net flux because this environment is at equilibrium. We have equal amounts of this substance dissolved in the extracellular fluid and the intracellular fluid. And we're starting to pack stuff into side weave. Okay? So this would require energy in some form. We then see that we can start to have other situations where we're moving stuff in two directions. Two directions can still be active transport. We'll talk about some examples of that. Okay. So when we're thinking about a pump, something that is performing active transport, we're thinking about the fact that it's a protein. So it's going to be a protein embedded in the phospholipid bilayer. It's going to go all the way across. So it's an integral membrane protein and it's a transmembrane, goes all the way across membrane protein. It's functioning as a transporter, kind of like as a carrier. It's also functioning as an enzyme. So specifically the enzymatic function here is breaking something down for the energy, so harvesting energy. So the most important pump we'll talk about in this course really is the sodium potassium pump. This sets up a lot of the function of cells. So this is the one that you have a picture of here. Sometimes it's called a sodium potassium ATP ACE. And that ACE gets to its enzymatic function, which you can see happening here at the bottom of the picture of the pump. So the enzyme function is that it's taking ATP, breaking it. So that's the enzyme part, leaving you with a phosphate and ADP. So we have two things going on here. So a pump can harness energy, usually in the form of breaking down ATP, getting the energy out of that last bond between the three phosphate groups. Pump is also going to have specific binding sites. So it's going to have pockets where something fits in, something binds in. And this means because we have specific pockets, like our carrier proteins, we can have these proteins be saturated. So we can have them be full because they only have so much space. So that's different than a channel, which is just open as long as it's open. So here we see sodium, free sodium binding into the sites for sodium, coming from this intracellular side, and we see the ATP getting broken down, beginning the action of this pump. So we're going to be separating out our understanding of primary active transport versus secondary active transport. In primary active transport, you're going to really directly see that use of energy. Secondary active transport is going to be a little more subtle. Secondary active transport usually happens after primary active transport has happened somewhere in the cell, and then it uses the energy that's stored in a gradient, so in a difference across the cell membrane, to power the movement of something else. Sometimes I like to think about it shorthand as if you're looking at secondary active transport, you're going to expect to see a second molecule involved. Okay. But that's not hard and fast. That's your second thing you're checking because some of our primary active transport examples, including the sodium potassium pump, which is really important, do involve two different ions, two different molecules, but we can tell that they're primary active transport because we directly see that energy input. So in primary active transport, we're going to see directly that source of energy. Usually this is going to be ATP hydrolysis. So we're breaking down an ATP molecule, which would involve putting in water. Water likely is not going to be drawn on. We just expect there to be water because we are in either the intracellular fluid or the extracellular fluid. Both of those are aqueous environments, fluid environments. So both of them contain water to begin with. So let's walk through this whole picture of the sodium potassium pump because it is so important. So what we're looking at here is a sodium potassium pump across our phospholipid bilayer, across our cell membrane. We see our intracellular fluid on the bottom in this beige orange color, the ICF. We see the extracellular fluid, the ECF, in blue up here at the top. So we can see that the first thing that happens is that sodium binds in to those three pockets for sodium here. So those are those three kind of binding sites for the sodium. We saw that on the previous slide. And then we see the use of energy in this time point B. So we see ATP being broken down, turning it into its lower energy form, ADP, adenosine diphosphate. We've broken off this phosphate group and actually tacked it on to our sodium potassium pump for a little while. So we put in the 3 sodium. Now we've broken down ATP for energy. So at this point, when we break down that ATP for energy, this causes a conformation change, so a shape change of that transmembrane protein, which puts sodium out into the extracellular fluid here. That sodium is released now, but we're not done. The second piece that is going to happen has to do with potassium. So we're going to want to go all the way back to our starting state. So what happens next? So we now have 2 different pockets exposed. So these 2 pockets are now available for potassium to bind into. So they have different chemical properties. So sodium isn't going to bind back into them. They're specifically for potassium. Specifically, it's for 2 potassium ions. So we have 2 potassium ions bond in. That phosphate group that we broke off from the ATP at this point dissociates, so it kind of falls off. And that causes our protein to flip its shape back with these pockets facing the inside of the cell, facing the ICF. So at that point, potassium is released into the cell. So you can notice here that sodium, we're sending 3 sodium out of the cell here, and we're bringing 2 potassium into the cell. So as we move forward, we'll also think about the implications of this for our electrical charge across the cell membrane, because essentially we have exported a charge, right? We put out 3 positive ions, brought in 2 positive ions. So we essentially lost 1 little positive charge to the external, or the extracellular fluid in this case. Okay. So that is an example of primary active transport, because we saw that pump, that word pump usually also tells us that it's primary active transport because a pump directly uses the energy. Secondary active transport, energy is going to be released from the diffusion of really an ion, usually sodium. This is secondary active transport because the first step of this would have been to use, for example, that sodium potassium pump, do primary active transport and set up a gradient. So we saw that we were pumping all those sodium out of the cell, right? We were using energy to do that. So we know that was against the sodium gradient, against the way it wanted to move, against the electrochemical driving force. So then we have those sodium hanging out unequal on either sides of the membrane, not at equilibrium, and they want to move. So they have that electrochemical driving force, basically sitting there waiting to be released, waiting to allow them to move. So in secondary active transport, we let them move. Remember, an ion can't cross that cell membrane unless you let it, unless you have a protein that allows that to happen. So you can control the movement of ions by controlling the state, open or closed, of those proteins, or overall their presence in the membrane at all. So in the secondary active transport, we set up a sodium gradient. So we'd have high sodium outside the cell. We have low sodium inside the cell. Right. So we can see here that sodium is moving the direction it wants to go. Okay. We know this is actually a little more complicated. We'd actually want to know that this is the electrochemical driving force, but we do often just shorthand it anyway with our concentration gradient here, because the inside of our normal cells at rest is -70 millivolts. So that direct chemical driving force and electrical driving force for sodium specifically is usually the same direction. So we have sodium moving the direction it wants to go. Okay. That's why this arrow is green here in the drawing. It tells us sodium is going its preferred direction, going with its driving force. But glucose here has a red arrow. So glucose, we would only be worried about its concentration gradient because it doesn't have a charge on it. It's not an ion. We don't have to worry about the electrical driving force. So we're just worrying for glucose about a chemical gradient, about the chemical driving force, about its concentration. So for glucose, we see this as a red arrow, so we know it's against its preferred direction. So this would tell us that we're going to an area of high glucose concentration from an area of low glucose concentration. So we're essentially like shoving it into a very packed bus, a packed subway car, right? We're shoving everything into where we already have a lot of it. It doesn't want to do that, which is why we need a source of energy. And in this case, the source of energy is not directly ATP. The source of energy is that sodium gradient. So you can think of it as sodium kind of grabbing the glucose and pulling it along with it in this case. Okay, so as sodium is going the direction it wants to go, it's pulling glucose with it, even though glucose doesn't really want to go that way on its own. So that's why it's active transport, is because it required the energy input somewhere to create that sodium gradient. Or you can think of that movement of sodium as essentially like the release of potential energy or kinetic energy across the membrane. And you can think of that physical movement of sodium as the energy that we're using to move the glucose. So that's really our definition of secondary active transport, is that we're relying on previous active transport, previous primary active transport that's set up some type of gradient that we can then harness in order to move this second molecule. So sodium linked glucose pumps are an example here. They do the secondary active transport of glucose. So as I just drew on, we have a sodium gradient that we've set up already previously. That would have been step one. We probably did it with that sodium potassium pump that we looked at as our main most important example of primary active transport. And as sodium diffuses, that movement of the sodium with its electrochemical driving force, so in the direction it wants to go, that pump is actively transporting glucose along with it against the glucose concentration gradient. Questions about this setup and link between our primary active transport and our secondary active transport? Hopefully we have seen this before. Another example here would be a sodium linked proton pump. So as you can see, sodium is in this again. Sodium is a really important ion in physiology. It is often our source of energy. It's usually because we have set up that sodium gradient using the sodium potassium pump, which is primary active transport. So again, we see that we've set up a sodium gradient. Sodium's moving the direction it wants to go. And in this case, we're using that sodium gradient to move the ions. So we're moving them against their gradient, against the direction they want to go. So we would know that our electrochemical driving force points in the opposite direction. And if we just wanted to think about concentration gradients as kind of shorthand, we would think about pushing those hydrogens towards an area of high hydrogen ions from an area of low hydrogen ions. Although we know now that there are sometimes other details we have to take into account when we're thinking about hydrogen particles. Still secondary active transport, because we use a gradient of something else in order to actively transport those hydrogen ions in the opposite direction from where they want to go. This is just a big table from your book about all our different types of transport. So we have our simple diffusion, which I think we can include in this passive transport, even though the line doesn't go that far. So you can see our passive transport going down, our electrochemical gradient. You can see our active transport going up. We can see what type of protein is involved. We can see whether we need energy, the source of the energy. We can even see some examples, whether those proteins can get full, how specific they are to the molecules that they're moving. If you like studying in table form, I would pick the parts of that table that correspond to facts that we had in the slides. So that brings us to coordination between active transport and passive transport. So when we're thinking about a whole cell, okay, we're not going to have just one thing moving across that membrane at any moment in time. We have all sorts of cellular processes kind of happening at once. Okay? So we know from the very beginning of this unit that we have different concentrations in our different fluids. So we have different concentrations of our ions and our other molecules in the intracellular fluid inside the cell versus outside the cell in the extracellular fluid. The reason we have those differences, the reason we have things not at equilibrium, is that we are actively using energy to change those two environments, right? We have conditions we want to maintain inside the cell, right, for different cellular processes inside the cell. We even have concentrations we want to maintain outside the cell, right? We want to maintain our blood chemistry kind of stable. The blood, the plasma, is a type of extracellular fluid, just as an example. So we have this coordination between our different processes happening. They get kind of complex. Often we think about things being set up by our sodium potassium pump. So I'm actually going to circle this right here on the left here. So we can see that the sodium potassium pump actually set up multiple things for us, right? So it set up a sodium gradient, right? So it created the sodium gradient that we often use for active transport, packing a high concentration of sodium outside the cell, low inside the cell. We also actually created a potassium gradient in the opposite direction. So here we have potassium packed inside the cell, less potassium outside the cell. So if we wanted to have just passive transport of those two ions, we could do that. And we will talk about that when we think about our neurons. So our neurons are going to release these gradients, allowing those ions to move in the direction they want to. So the direction sodium wants to. So this would be a channel protein, a picture of a channel protein. This is just passive transport of sodium this time. Green arrow, we let sodium go the direction it wants to go. Same thing with potassium. This would be an example of a potassium channel. We just let potassium go where it wants to go. So we don't always have to do secondary active transport after we set up those gradients. We can just at some point release it and let the ion do its thing. All right, so we have a couple practice questions now. So we want to make sure that we do remember a little bit about rates. So our rates, I'll touch back on our facilitated diffusion. Remember what facilitated diffusion was from last time. What we would have wanted to know to answer this question is we're thinking about facilitated diffusion. So facilitated diffusion was one of our types of passive transport. So specifically, it was passive transport. So our molecule is going the direction it wants to go, but it's facilitated. You need a facilitator. You need something to make this easier. We need to go through a protein. Specifically, facilitated diffusion happens through a carrier protein. So that's why we have our carrier on here to answer A. So our carrier proteins have a certain rate. They need to flip across the membrane. They have a certain amount of time that takes. If they flip faster, your rate is faster. When we're thinking about the cell, right, if you have more of these carriers, you are able to transport more of that substance. So that's why the number of carriers in the membrane matters for our rate. And the magnitude of the electrochemical gradient of the substance would also matter because it wants to move, then there's a greater force essentially for that movement. The reason the solubility doesn't matter is that these molecules, if they're doing facilitated diffusion, we already know they're just not soluble across that membrane. So we already know that we have a molecule that can't cross that double layer of fatty acid tails. So a molecule that can't cross that hydrophobic region. We might also try to predict what happens when we have fluid accumulating the lungs. And I'm telling you that this decreases our capacity for delivering oxygen. So I want you to predict why this might be the case. Prediction, I'm going to click through. So the reason for this officially is that is essentially acting as an increase in the membrane thickness here. So oxygen is lipid soluble, so it's a small non-polar gas, so it can get across our phospholipid bilayer just fine. Oxygen can travel through fluid, so it can travel through the water. But when we have fluid accumulating, it can create kind of a thicker layer for the oxygen to cross. And really, this is just a reminder that membrane thickness does sometimes sort of vary and would affect the rate of transport. So here, for just simple diffusion, we don't have to worry about concentration gradients. relating to the permeability because it either is or is not permeable. Right? That there's kind of a yes or no here version. The concentration gradient is going to affect the rate, but it's not like if you have more of that molecule waiting to cross, the membrane is suddenly going to develop a bunch of holes in it. So the things that affect permeability have to do with the actual like chemical and physical properties of the environment. Because we're thinking essentially, how many gaps does the membrane have for that molecule specifically? So we are going to move forward and talk a little bit about osmosis as our final topic for this unit. When we're talking about osmosis, we are talking about the movement of water, what we know about our cell membrane. But technically, if it were just phospholipids, it would not be permeable to water, but almost every cell has aquaporins in it. So for shorthand, we are going to say that our cell membrane is permeable to water. But we know that there are lots of things that can't cross that cell membrane unless we let them. So in general, we're thinking large molecules, often glucose. We're thinking things like ions, things with charges on them, are really not going to be able to cross that membrane unless we let them. So we think about the membrane as being impermeable to those substances. So our polar molecules, our larger molecules, and our ions. So in situations like that, we are going to still want to try and reach equilibrium, right? It's like chemically, biologically, that the cell is going to try and even out the concentrations and forces for the across its membrane anyway. So the way it does that is by moving water instead of moving those things to which the membrane is impermeable. So when we can't move, say sodium, when we can't move an ion across the membrane, we may move water to kind of change the concentration of the sodium by watering down that environment, so diluting it, even though we didn't actually move a sodium ion itself. Okay. So here we have some definitions to think about. So when we're talking about impermeant solutes, impermeant means something that can't move across. So the membrane is impermeable to an impermeant solute. Okay. And we are thinking about the concepts of osmolarity and tonicity. So to understand osmolarity and tonicity, you have to realize that we can measure these concentrations in a measurement called a milliosmol. Actually, make sure, is this where your next set of slides starts? No, it's not. That's what I was wondering. Okay, let me go back to your section then. I feel like we missed a couple of things. Okay. We're on membrane transport part 2. Okay, we did that. Oh, yeah, right there. Something seems like it moved to the end there. Where is that? Nice. That was a lot of me talking without those definitions written here. Okay, so osmosis, our definition is moving water across that membrane. Okay, so this movement is going to be passive. We don't have to worry about membrane potentials. What we do want to think about is water gradients and solute gradients as well. I will add on to this. And honestly, I do find it easier to think about the solute gradient than the water gradient. But we want to, at least on a conceptual level, understand both. So what we're thinking about when we say the water gradient, we have something dissolved in the water, say an ion, okay, so some type of solute. So that solute occupies space, the water occupies space, and you can think of them as a trade-off. Okay. So osmosis is passive, so water is moving from areas with a lot of water, so high water concentration, to less water, lower water concentration. But because we have a trade-off between the solutes and the water, I do think it's easier to look at the solute. So you want to realize that in an area where there's high solute concentration, that means low water because those solutes are taking up space. Okay, so you can identify this either way, looking at either the solute concentration or thinking all the way through a problem and thinking about the water gradient. Often that seems like an extra step that is not always necessary when you're just trying to identify the direction. So we're going to say with the water gradient, so technically it's passive. If you just have solutes labeled, they're opposite to the water gradient. So you can think of things as moving towards areas of high solute. So water is going to be kind of sucked towards things like ions. So what we're looking at here is we have pure water versus a cell that has some solutes in here occupying space. So it has a little less water because it has less physical space for water. So our water gradient would be high to low. High water. Low water. Versus for the solutes, what I'm saying here, this is like high solute. Low solute. So water moves from high to low along its own gradient. But if you were to just see solute concentrations, you'd see that the water is moving towards the high solute concentration. So those two ways of figuring out the direction will get you to the same answer. We see the opposite situation in the bottom one. So we see water flowing out towards that greater solute concentration, that greater sucrose concentration in this example. When we think about osmolarity, so osmolarity is a measurement, an overall measurement of the solutes in a solution. Okay. So we're remembering that the solute displaces water, so we need space for the solute and we need space for the water. So when we're thinking about osmolarity, we want to know about everything dissolved in that water, not just one specific ion, not just one type of sugar. So to do that, we usually measure this in milliosmoles. To find those out, if you have something that's covalently bonded, so like a molecule of glucose, it's all one thing, doesn't separate out in water in any particular way. You can go 1 mole of glucose, going to be 0.1 osmol if we're in a liter of water. When we're thinking about ionic compounds, we do need to think about the fact that they separate. Those two components of that ionically bonded substance separate from each other if you drop them in water. When I say you have to add stuff up, you have to think about our sodium taking up space and also our chloride taking up space. Okay. So it works essentially the same. We're still dissolving it in a liter of water, but we're going to have two things in there. So we're multiplying by 2. So if we have 0.1 mole of NaCl all bonded together. Means we have 0.1 mole of Na, we have 0.1 mole of Cl. So we're gonna end up with 0.2 osmoles in total in the liter of water. So this is a measurement essentially of solute concentration in water that we can use to figure out which way water is going to move in a given situation. That's really why we care about it, because we're thinking about this essentially as a pull on the water, right? So if you have a higher number, a higher osmolarity, that's going to pull water towards it because it's really indicating that you have like a higher concentration of stuff dissolved in that environment, in that side of the cell. Okay, so that water is moving towards it to water it down. Usually, since these numbers are in decimals, not decimals, they're kind of ugly to look at in that version, so we move them into milliosmoles. A milliosmol is 1/1000th of an osmol. So these numbers are just going to be prettier and rounder and a bit bigger after we do that conversion. So the typical osmolarity of the intracellular fluid and the extracellular fluid, just so you know, is 300 milliosmoles. So just like I said, our normal typical cell, its resting membrane potential is -70 millivolts. We have a typical number we expect in our intracellular fluid and extracellular fluid. A typical number that we compare stuff to is 300. So when we're thinking about osmolarity, we're thinking about the movement of water. We can define what our relative osmolarity is, what our relative concentrations are inside the cell versus outside. Okay. So we do that by putting the word osmotic at the end. So this tells us that we would specifically be looking at like the osmol numbers. That's why we're putting osmotic here. Okay. And we can see the behavior of a cell due to the movement of water in each of these situations. We can start with isoosmotic in the center. So iso means same. Okay, so an isoosmotic solution would have the same osmolarity outside as inside. So that means if we have water moving, we're going to have the same amount going in as going out. So there's going to be no overall change in the size, shape of that cell, or in its essentially water content under these isoosmotic conditions. However, if we have a big difference in osmolarity across our membrane, the cell will respond to that because water is going to move as it's pulled on by those solutes. So as it's pulled on by that osmolarity. So in a hyperosmotic solution, so hyper is always going to tell you more, like something hyper, super extra solute concentration outside here. So hyperosmotic solution, we're going to think lots of solute concentration out here. So maybe instead of 300, it's like 400 or 500. We're going to have water move towards our greater solute concentration. So we're thinking lots of solutes outside. Hyperosmotic. This is going to lead to potentially crenulation. So you're going to be concentrating whatever's left in the inside of that cell. That's why the water is moving anyway. It's trying to reach equilibrium across the membrane. But that means as you're removing water, that cell is shrinking because the cell mainly made up of water. In a hypoosmotic solution, we have the reverse. So hypo is always going to be low. So in a solution with low osmolarity, that means we have maybe 1 or 2 solutes out here in the ECF. Maybe we're even in a pure water environment, but we have a lot more inside the cell. Lots of solutes, higher osmolarity inside the cell. This means water is going to be pulled on by that higher osmolarity inside the cell. It's going to move into the cell to water down that higher concentration of solutes. This is going to cause the cell to swell As you fill it with more water, that more water takes up more space. So the cell will swell and potentially burst. So it could potentially lyse if we swell it up too big. So when we're looking at these osmolar numbers, we'll often refer to the osmotic pressure. So we're thinking about all these solutes dissolved in here as pulling the water towards them. So pulling the water towards them. We refer to it as a pressure because it's technically defined as how much pressure would you have to put to stop the water from moving. But it's easier to think of that higher number as being a pull on the water. So you can see here the solute concentration, the osmolarity on the right, it's 500 milliosmoles. Compared to on side one, we have a lower solute concentration, a lower osmolarity, 300 milliosmoles. So you can see that the water is flowing towards that higher solute concentration, towards that higher osmolarity. And you can see that the osmotic pressure just has different numbers and units on it, but it is replicating that same that same kind of gradient, let's say, right? So for osmotic pressure, we're still moving towards this higher pull on water, essentially. So if you have a higher number, whether it's osmolarity or osmotic pressure, that's telling you that the water is being pulled towards that location. The only thing that would be the reverse is if you actually look at the water concentration. I do want to de-emphasize a little bit because while it's conceptually correct, almost nobody talks about it in that way in physiology. The numbers that you're going to see are these osmolarity numbers and sometimes the osmotic pressure numbers. So we will stop with these basic definitions for our osmolarity. So you do have an exam coming up on Monday next week, I believe. So the format for that exam, we've taken it in here, but it will be on laptops. So bring your own, we'll do it on your own laptop. If you don't have one, I'll bring in a computer card. If you have one that's broken or doesn't keep a charge or whatever, you can just borrow one. We'll do that. I like to put up a full-length practice exam, so that will be available for you to study from and get a sense of the coverage of the exam and the depth of that coverage.